Now, we will look at the fifth problem of the fourth tutorial. Here we have to go for that envelogram, and in this case of envelogram, that we are given 3 data files PEC1, PEC33 and PEC52. Okay. And to read that file and as well as plot, we are given a MATLAB file. Now, these 3 PCG files, phonocardiogram files, that we have to produce the averaged envelogram over the several cardiac cycles using ECG as a trigger. And another question we have, that because the cycles would vary, how do we handle that variation in the length of the signal from one bit to the other bit. Now, why average envelogram is actually requested? If you look at that the PCG signal, we have 2 variations, that one is S1 and S2. These 2 signals are there in the phonocardiogram. Now, out of these 2, that both of them, they are random in nature. So, the envelope what we create out of it, it has some amount of variation, and that if we use the average envelogram, we can get a better rendition of that, or better actually estimate of that S1 and S2, because if we take the cycles one after another, we can assume that the condition of heart has not changed from one beat to the other, okay, especially for the consecutive several beats. Okay. And as we are doing the averaging, and that if you look at that nature, that envelogram will be like, it will be one P could be here, another P could be here. It will be very much dependent on the position of this. Okay. So, for the averaging, just like synchronous averaging, we need to have a reference to actually align them, and in that case, that another challenge is there, that as the beats are not exactly equal, because ECG is a pseudo station, that it is not a exactly periodic signal, but nearly periodic or pseudo periodic signal. So, that there would be some variation in the length of the signal. Okay. So, in that case, that how do we take care of that? Okay. So, that is the challenge we face here in this case. So, first job, like all that assignments, that first we need to collect the data and the MATLAB file to read them, and we need to first keep the signal as well as the MATLAB code in the working directory of MATLAB, and then we start the exercise. First, let us remember that how do we create an envelogram. In case of envelogram, that what we are trying to do is that we have to, that if you look at the theory, what we are trying to get, we are looking for that analytic signal, and the amplitude of the analytic signal is providing us that envelope or envelogram. So, first we need to find out the analytic signal, and we know that some characteristics of the analytic signal, unlike our real signal, that analytic signal has only that presence in the right side of the frequency axis. Okay. That means, if we have a real signal, that say we have a spectrum like this, here is that amplitude and this is the frequency. Okay. If this is say xf, Now, corresponding analytic signal, the spectrum would be like this. That analytic signal does not have this actually any value in the negative side. Okay. Now, we are exploiting that fact to construct the analytic signal, and from there we find out the envelogram. Okay. So, the first step towards it is that we go for the DFT of the PCG signal. We can also employ FFT if we want fast computation. Now, DFT we have mentioned here because it is more generic, and what we have to do, that we have to put all the coefficients which are in the negative side after taking the DFT for a signal starting from length 1 to n. We know that the number of coefficients we get is also 1 to n, and in that scenario the negative frequencies are there from nearly half to the end, that is n by 2 plus 2 to n. Okay. So, that means that if we look at that sequence, if here is the middle, we are just starting from little after that and to the end. So, that part all the coefficients we are forcing to 0. Okay. And the positive part of it, that this part, that what we are doing, that from that part we are that we have to increase the value. Okay. And the first one, this is the DC value, that will remain to be the same. Okay. So, that is what we are doing actually step by step here. The next is the positive frequency terms, which are starting from index 2 to n by 2 plus 1, they are multiplied by 2. Okay. And the DC term 1 remains unchanged. Okay. So, that is the way we get now the spectrum of the analytic signal. Okay. The next is we go for the inverse DFT of the signal. That means, we started with a real signal, in this case it is PCG, which is our signal of interest, and we have created that analytic signal in between in the frequency domain, and when we take the inverse DFT, we get the analytic signal in the time domain. And next point is that we have to look for the magnitude of the resultant signal, that will provide us the envelogram. Okay. That the analytic signal what we got, the amplitude will give us the envelogram. So, for that what we have to do, we have to take actually that absolute value of that, because this one would be a complex signal. So, if we take the absolute value of it, we will get that magnitude, and that is what we are looking at, that provides us the envelogram. Now, let us proceed. We first go for the Pan-Tonkin algorithm for the Lehner-Rangayan algorithm for detection of the QRS complex and dielectric notch. Now, why we are doing that? We know that the bit location varies from actually cycle to cycle. So, in this case, that S1 and S2, these two signals of the PCG, their location also will vary. So, first we have to find out those location, and for that we need to find out the location of the ECG signal, and for that we need the Pan-Tonkin algorithm, and Lehner and Rangayan algorithm will help us to get that dielectric notch, and from there we can get the location of S2. We have already discussed these points in the previous assignments. So, here what we show at the top, that we have the PCG signal given, we have marked S1 and S2 location, and how do we get that? We get the S1 location that is given by the R point in the ECG signal, which we could recover using the Pan-Tompkins algorithm, and for the dielectric notch we have used the Lehner and Rangan algorithm, which is given below, that here. So, that from there the dielectric notch, that we are getting the location of the dielectric notch, and that gives us the that S2. Okay. So, these two parts we have actually collected from these signals. Okay. And once we get that, we know the span of importance of the PCG signal. Now, if we look at in between, that this part, for example, this is, there is no actually activity. So, there is actually that whatever the signal is there, it is noise. Okay. So, these portions, it is better that we throw it away and do not consider for getting the envelope, because that is the noise floor. Okay. And here another thing we notice here, neither the S1 and S2, they are looking exactly the same. If we look at this one, that S1, the next cycle S1, nor they are exactly periodic. The difference between the two bits, they are not exactly the same. So, that gives rise to the challenge, and it needs that we need to always take the help of the ECG signal and find out the R location to find out the location of S1, and that for the S2 also for each cycle. Now, let us proceed, that this is for the first signal, that PEC1. Let us see that what happens for the other signal, and how do we first find out that location. Now, what do we do, that here we are assuming that we already know that Pan-Tompkins algorithm, and from there we have the R location already found. Okay. And the location of dielectric notch is also found, as we have done the assignments earlier. So, those codes are with us, we have found these two. Now, using that, what essentially we are trying to do, we are trying to take, if say this is that S1, this is S2, we are trying to take a segment like this, somewhat starting before S1 and going after S2. So, for that what we are doing, we are taking R location minus 150 samples, and we are going that dielectric notch location plus 400 samples. Okay. So, that way we are taking actually somewhat more than the exact S1 to S2, because there would be some spread of the signal. So, we are trying to make sure that we are not losing out anywhere because of the measurement error. Okay. So, we are taking this span, and that part of that signal, PCG signal, we are actually taking cycle by cycle. Okay. This for loop is to actually store those locations, that multiple bits or multiple cycles of that PCG signal, and at the end of it we take the maximum length of actually these signal segments. Now, what it gives to us? It gives us that what could be the maximum length. So, first we provide a container, that segmented PCG, fill it with zeros, okay, that the number of the length, we know that how many cycles are there, that is one variable and another is that maximum length. And now first attempt in the for loop we have calculated only the length of that range. In the next one we are actually collecting that part. After we know that what is the maximum length required, we are just picking up that part from the PCG signal, okay, and storing it in segmented PCG. And each of this row, this I variable, it is giving actually the index of the cycle. Okay. We are collecting the data of over multiple cycles. So, that is what actually we are storing it for them, because we would need them to calculate that envelogram, and once we have the envelogram of each of these cases, then we can actually average them to get the average envelogram. So, let us proceed for that, and we see that first that once we have the length of the bit, then we have to find out that how do we take the Fourier transform, and invariably that we are looking for that FFT for that purpose. And we know for FFT that power should be of 2 to the power n, the length should be of 2 to the power n. So, we are trying to find out that what is the length of it. For example, in this case the length is, the maximum length is L, that is 900. So, next value which is 2 to the power n is actually 1024. How do we find it out? We can take the log to the base 2 L, and we can take actually ceiling of that to give us n, okay, and that n we can take that to compute the 2 to the power n. So, this whole operation is done by actually this line, that next power 2 L, this is actually computing this part, that ceiling of log of L to the base 2, and then we take 2 to the power of that quantity. So, we are computing that 2 to the power n here, and we are get that number of coefficients or length of samples for FFT. Okay. We are storing in that variable NFFT. Then we are computing some variable L2 which will require for the computation, for ease of actually remembering that we have that something we have taken that length by 2 plus 2. So, that and from there to the end. So, we are taking actually that length as L2. Okay. That will help us to do some bookkeeping. Now, the first job is that we need to take the Fourier transform of each of these that PCG segments or each of the cycle of the PCG that which are padded to some extent if they are less than L, and beyond that also it could be actually padded, and we are taking NFFT point FFT. In fact, if we have decided about it that we are using NFFT, then we could actually compute this NFFT and we can directly take actually that NFFT as the L in the previous case, and that both the jobs could be done together itself. Okay. That here when computing the FFT, that first actually this subroutine FFT, it pads it further if it is less than actually NFFT. That means from 901 to 1024 it will pad with 0 and then compute the FFT. Okay. And that once that is done, in the that segment that in the that variable b, what we are keeping? We are actually keeping the coefficient. These are the A is the coefficient of the Fourier transform of the PCG signal, that is a real signal. Now, the corresponding analytic signal that in the frequency domain is BB. So, we are taking the DC coefficient that is not changed, that positive coefficients it should be actually multiplied with 2, that is starting from 2 to NFFT by 2 plus 1, and then we need to have the remaining part should be zeros. And then once we have that we have to take the IFFT of that to get the that time domain signal, and absolute value of it will give us the magnitude. And this part is very necessary, because as this is a analytic signal, in the time domain it will give us a complex signal, not a real one. So, if we want to know the magnitude, we need to take the absolute value of it, because the number should be the complex number. And once we have that this envelopegram for each of these cycle, then we can take them together and compute the average, okay, by using the command min. Okay. So, that is the simple algorithm here, and that is the way we calculate the average envelopegram. Let us see that how the result we get. We for that we plot the envelopegram and average envelopegram using the subplot command. So, first we take the that first PCG signal PC1 dot dat, and here we have taken just one single cycle to give a better rendition. If we take all the cycles, that will get the whole signal, but none of these cycles will be clear. So, in this case we get that this is the S1 and this is the S2 part. Corresponding envelopegram we get here. Now, out of it, if you look at that S1, that it has lots of variation here, this part especially. So, that once we average it over number of cycles, we get that it becomes much more smooth, and we get actually much better actually envelope. And correspondingly, the perturbations outside actually that S1 and S2, they are also reduced to a good extent. Okay. So, that makes a that envelope more actually that that appropriate for representing the signal. Now, let us look at the next actually point, that in a similar way we find out for the that PEC33 and PEC52 dot dat. So, for the PEC33 dot dat, again we start from the beginning, that we need to find out the that R wave from the ECG signal. So, we have marked them with the triangle, and from there we have taken here that the location of the S point, we have marked that, and for that next we have taken the carotid pulse and we got the location of the dielectric notch. From there we got the S2, and you see in this case that S1 and S2, that a lot of I think murmurs are there, that signal seems to be merged actually to some extent. Okay. So, in any case that way we could find actually the span of the that each cycle of the PCG, and from there we could actually get the envelope. In this case, as the variations are more, or S1 and S2 are more jagged, as we can see it here, that it is much more jagged. We have the envelope also like that. Okay. In fact, in intermediate portions also you see that lot of peaks are there. However, when you go for the average parallelogram, that S1 and S2, they are coming much more prominent way. Okay. So, that is the benefit of, I would say, that going for the envelogram to average envelogram. Now, let us look at the third one, which seems to be again a better signal, where S1 and S2 they are limited in time, and again we follow the same procedure, that first we look at the ECG signal and we get the R wave, from there the location which gives us the location of S1, and from the carotid pulse we get the location of the that diatrid notch which gives us the location of S2. We have marked them, we find out that each cycle, and from that we could compute the envelogram and that average envelogram. Okay. And again what we notice that the kinks what we had, for example here, those things are actually minimized in average parallelogram. Okay. So, here that dips were there, they have become actually minimized, we get a much more stable shape in case of average parallelogram. Okay. So, that is the way we are successful in computing them, and at the end of it we need to have some observation that what we learn out of this assignment. The first thing, that for average envelogram, the zeros are padded to deal with the situation of unequal number of samples in the ECG beats. Its cycles are different in length, and that to avoid the numerical problem in averaging the cycles which are of unequal length, what we do, we add zeros at the end, what we called as padding, and make them of equal length, and that makes it easy for us to take the average. Okay. So, that is the first part. In fact, that was one of the question we are asked to answer. The next point is that the variation in average envelogram is smooth, that averaging is actually helping us to that subdue the variation, and that has a positive effect in the getting the envelope of the signal. Okay. So, that is the benefit we get out of the average envelogram. Thank you.